Hello, my name is Harry Chen, and I will be covering this CNCM lecture on polynomial transformations. The prerequisite to this lecture is knowledge of Vieta's formulas. If you did not know those already, CNCM has already covered a lecture on it, so check that out. So, polynomial transformation relies on transforming the polynomial, obviously. So here's the first example of how we may do that. So for this specific example, it's kind of trivial, as you can just obviously just use Vieta's formulas directly to find alpha plus beta and then just add 2 to that. However, we're going to use polynomial transformation on it. So the gist is that we want to find the polynomial with the roots alpha plus 1 and beta plus 1. And so to do that, we know that alpha and beta are roots of this polynomial here. So we can shift this polynomial by -1 like so. And then if we substitute in alpha plus 1, then into this, into this polynomial, then what happens is that we see that it becomes alpha squared minus 17 alpha plus 21. Well, that's exactly what we have up here. And so alpha plus 1 has to be a root. Alpha plus 1 has to be a root of this polynomial. Likewise, if we plug in beta plus 1, we get the same thing. So this polynomial has roots alpha plus 1 and beta plus 1. What do we do with this? Well, let's try expanding it first, because this is a little bit ugly. So we should get x squared minus 19x plus 1 plus 17 plus 39, I believe, is equal to 0. So now to find, we just want to find the sum of alpha plus 1 and beta plus 1. So that's the sum of the roots of this equation. So we can just use Vieta's formula. So that's just negative 19 over 1, and we're done. That's just equal to 19. So this was kind of a silly example. Of course, this was kind of unnecessary. However, it does show what exactly polynomial transformation is supposed to do. It's supposed to get new roots using the roots that we already know of, and then typically we'll apply Vieta's formula in order to solve. Here's the second example. Given that alpha and beta are the roots of x squared minus 21x plus 3 is equal to 0, compute 1 over alpha plus 1 over beta. So again, if you watch the Vieta's formula lecture, you might be tempted to just use Vieta's formulas, which you absolutely can. However, we're going to use polynomial transformations. So in this case, it's a little bit hard to make a polynomial whose roots are 1 over alpha and 1 over beta. However, here's the kind of the trick we'll do. We want to find out what the inverse of 1 over alpha is. So the inverse of 1 over alpha, well, that's just equal to, again, 1 over alpha. That's the inverse. And so we can substitute this 1 over x into this polynomial up here, and we get 1 over x squared minus 21 over x plus 3 is equal to 0, right? Now, it's pretty obvious that 1 over alpha and 1 over beta are roots to this, because if we plug that in, then we get alpha squared minus 21 alpha plus 3, which is what we have up here again. So this is the polynomial we're going to work with now. Now, we want to use Vieta's formulas on this, just like the last problem. However, that's kind of not possible right now, because this isn't really a polynomial, because the powers are less than 0. So to do this, to remedy this, we're actually going to multiply both sides by x squared. If we multiply both sides by x squared, we get 1 minus 21x plus 3x squared is equal to 0. So now we can easily verify that 1 over alpha and 1 over beta are still roots of this. Because we plug that in, we get kind of we get like 1 minus 21 over alpha plus 3 over alpha squared. However, we can multiply alpha by both sides, assuming alpha is not 0, which it can't be. 0 is not a root of the original polynomial up here. And then we just get the results that we got up here, and so it's a root. And so now we know that these two are both roots of this polynomial, so we can just use, well, Vieta's formulas. So the answer is just 21 over 3 is equal to 7. this was a kind of clean way to do this problem that didn't really require a whole lot of arranging or adding or anything. So it's a nice way to do it, and that's typically how polynomial transformations work. Usually you can always do a polynomial transformation problem without actually transforming it. You can typically just use rearranging in V8s. However, polynomial transformations can make things faster sometimes. This problem is very similar to the last problem, only it's alpha plus 1 over alpha plus 1. So we're going to use essentially the same tactic to tackle this one. Let's try to find the inverse of 1 over x plus 1. That's just 1 over x minus 1. You can check that for yourself to see that these are inverses if you want. I'm not really going to go into that. But anyway, so that means we can substitute 1 over x minus 1 into this equation, and we get 1 over x minus 1 squared minus 21, 1 over x minus 1 plus 3 equal to 0. From here, we can just do some, we can just expand this out, and we should get 1 over x squared minus, should be 23 over x, I believe. And then plus 25, I think it was. I think it's 25 is equal to 0. Now we're going to use the same trick as before. We're going to multiply both sides by x squared, and we should get 25x squared minus 23x plus 1 is equal to 0. And this is pretty simple to do. We just use the formula one more time, and then we get 23 over 25. So this problem is just putting it all together into putting lots of problems together into a slightly more difficult expression. It's still not that difficult though. But yeah, it's you can see again, you could probably use V8s on this, just cross multiply and then not cross multiply, combine like denominators and whatnot. But this is a nice solution as well. This is an interesting twist on the previous problem. Instead of 1 over alpha plus 1, it is alpha squared. So let's just try exactly what we did last time. So what's the inverse of x squared? Well, that's obviously just going to be plus or minus square root of x. And so if we substitute that back into this, we get x minus plus 21 square roots of x plus 3 is equal to 0. Well, this is not great. How do we use V8s on this expression? Well, the answer is we cannot. There's basically no way to. So this is actually dead end. This solution will not work because this is no longer a polynomial, because this is raised to the power. This here is raised to the power of 1/2 instead of an integer, and so this solution won't work. Let's cover an actual solution that will work to this problem on the next slide. So what is this alluded to actual solution? So if we noticed, when you square a number, the sign of the number doesn't really matter. So so alpha squared is the same thing as negative alpha squared. We are going to take this to its, we're going to take advantage of this. So we want to construct a polynomial whose roots are alpha, beta, negative alpha, and negative beta. You'll see why in a second. When we do this, we know the polynomial with roots of alpha and beta is just x squared minus 21x plus 3. Well, the polynomial with roots negative alpha, negative beta will be if we plug in negative x into this polynomial here, and so we get x squared plus 21x plus 3. And so this polynomial will be this huge polynomial here will be the polynomial with roots of all 4 of these. So this is actually going to be equal to x to the 4th. X to the 4th. Well, the x cubed terms actually cancel out, so there won't be an x cubed term. For the x squared term, it's going to be, let me see here. Should be minus 230. Oh, not 235. 435x squared plus 9. So now, what do we do with this? So since it has roots of alpha, beta, negative alpha, and negative beta, what we can do is now we can actually make the substitution of plus or minus square root of x. So this becomes just x squared minus 435x plus 9 is equal to 0. And so why can we just go between these two? The reason is because okay, so the reason is because the roots of this, so the roots of this polynomial are going to be alpha squared and beta squared. Well, alpha squared and beta squared, well, there's two possibilities for what alpha and beta could be in both of these. It could be plus alpha or minus alpha, plus beta or minus beta. And so when we do plus or minus square root of x, both possibilities are included for. And so this condenses the two alphas together and the two betas together, and so we just get alpha squared and beta squared as the roots of this. So now we can just use these formulas pretty simply. So our answer is just 435. It's a miracle that this works, but it does. And it's probably way easier to just use Vieta's formulas. But this is a cool application of polynomial transformation. It requires some ingenuity. So it's pretty cool. This is a bit of a weird one. So it says compute the following expression. The sum from n equals 0 to 4 of 1 over e to the 2ni pi over 5 plus 1. So if you don't know, e to the 2ni pi over 5 is a complex number. It's the exponential form of a complex number. It's essentially saying, cis 2ni pi over 5, if that's more familiar. But anyway, this problem is weird in that it's not like the other polynomial transformation problems we've seen so far. It kind of goes in reverse. So it doesn't give us a polynomial. Instead, it gives us what we're going to call it's the root. So one of the important things about this problem is that this here is actually a root, no matter all of e to the 2n, I'll write like this, 2 pi in over 5. These are all roots of x to the 5th is equal to 1. These are all roots of unity of x to the 5th equals 1. That means we can actually use this polynomial, x to the 5th equals 1, as the polynomial we're going to transform. So let's do that. The inverse of 1 over x plus 1 is going to be 1 over x minus 1, as we showed in the second problem we did. The third problem we did. And so we can just substitute this into here, and so we get 1 over x minus 1 to the 5th is equal to 1. We're actually going to multiply both sides by x to the 5th right now instead of later, and so this becomes 1 minus x to the 5th is equal to x to the 5th. And so this becomes 2x to the 5th minus 5x to the 4th plus 10x cubed minus 10x squared plus 5x minus 1 is equal to 0. So now this expression here is kind of hideous, but we know that we just need to use Vieta's formulas on this because this is the sum of all of them. So therefore, the answer is just pretty easily 5 over 2. That is our answer. This is probably one of the better uses of polynomial transformations because I bet that it's really hard to just directly use Vieta's formula on this, and probably would be very annoying to do. So, this is kind of a nice way to do it. But anyway, this is the last problem that we're going to do for this lecture. If you want to know more about polynomial transformations and function transformations in general, please check out the handout linked in the description. I unfortunately had to cut out a lot of that for this lecture due to time constraints. But yeah, if you like this video, please subscribe, like, do whatever you want really with the thing, with the lecture, with the video, and then yeah. So thanks for watching, and do the POTDs.